In the world of human-machine interface, prosthetics have a need to be ever improving, as we increasingly try to mimic the natural functions of the human body. As of 2017, there are 2.1 million people living in the USA with limb loss, excluding fingers and toes. That is the equivalent to a third of the population of New South Wales, with the number increasing by 185,000 every year. Globally, there is the equivalent of one amputation every 30 seconds. There are several reasons why amputations can be necessary, including cardiovascular disease and traumatic accidents. Other reasons also include infection, tumours, nerve injury, and congenital abnormalities. Though Australia has the second highest rate of diabetic-related amputations in the world, most prosthetics are necessary due to traumatic experiences such as car and workplace accidents and the effects of war. From a historical perspective, the earliest prosthetic ever discovered was a false toe for an Egyptian woman, dating to as early as the 10th century BC. The toe was necessary functionally to wear sandals, the fashionable footwear. Prosthetics have historically primarily come about during times of war, when the loss of limbs was most common. In the early days, artificial limbs were usually hooks replacing a missing hand, or wooden replacements for amputated feet. These provided some function and catered to aesthetic sensibilities. These early prostheses were improved upon over time, enabling more numerous and more effective functional benefits. In time, mechanical features such as hinges and locking joints were developed, mostly in hand replacements. During World War II, major strides were taken in the advancement of prosthetics, and the field saw the introduction of hinged knees and hands with the movement of individual fingers. Modern prostheses have increasingly tried to mimic normal function of natural body parts, but normal function has proven tricky to replicate. Neuromuscular function of a natural arm, for example, involves not just movement, but multiple processes. Say you want to pick something up. The process of planning begins in the anterior frontal lobe, where decision-making primarily occurs. From there, the signal is passed to the premotor area, where preparation for movement is performed. Current sensory information about limb location and part of the processing of movement guidance is performed here. This works in coordination with the primary motor cortex, which is the origin of motor impulses down the spine. From there, the signal is passed through the cerebral peduncle in the midbrain to the medulla, where it passes contralaterally to the other side of the body and down the lateral corticospinal tract. It leaves the spinal cord at the brachial plexus and descends to the musculature in the arm, where muscles are told to relax or contract, depending on their part in the movement. As movement continues, sensory feedback from the muscles regarding their state of strain and stretch, from the joints regarding their location, and from the skin regarding the pressure of your hand on the object, is fed back up to the brain via the dorsal column medial lemniscus pathway, or just to the spine for the myostatic reflex, where choices about reach and necessary grip can be processed and acted upon. Unfortunately, until very recently, this level of responsiveness and feedback has not been possible from prosthetic options. Today, the most advanced artificial limbs are those such as the modular prosthetic limb created by the Johns Hopkins Applied Physics Lab, which moves but with directed thought. In order to use it, the patient must first have a procedure in which a doctor translocates the residual nerves to other muscles, either in the stump of the arm, or, in the case of higher amputations, in the chest. These nerves innervate small areas of these muscles, as they would if they were still attached to the natural hand. These muscles act as amplifiers for the signal, and the prosthesis detects them with the use of an integrated EMG. There are now even prosthetics which enable sensory feedback to the user through a similar process of translocation of nerves to sections of the skin. These patches of skin map to the fingers and allow sensation of pressure or grip. As a result, the person can now not only carry out basic functions using the artificial hand, but more complicated tasks. These high-end interfaces are not available to the broader community yet due to their high cost, but as they develop, costs are coming down. There are still issues with these limbs. Privacy protections are important, and these machines can potentially be accessed by hackers who can steal personal information and may be able to take control of the limb remotely. But these issues are being dealt with, and in time we are getting ever closer to prosthetics which are indistinguishable from the real thing.